So if you have any questions, I suggest that you hold off until the end. But unless Abdullah Mughis, unless he says that you can ask questions during the presentation, then you can ask questions during the presentation.
Yeah. I believe end
So
is a good one.
go,
At
what is
the end.
that?
I believe at the end is a good option.
Yeah, so leave your questions until the end, just make notes of them. And then at the end, you can raise your hand or write them into chat. So today's lesson is going to be on the intelligence of optimal control. I'll leave it all into your hands, Abdullah Mughis.
Okay. Thank you. Thank you. Okay. So, Bismillahirrahmanirrahim. I hope my slides are visible to everyone. Hi, everyone. I'm Dr. Abdullah Mughis, and the topic that we will be discussing today is the intelligence of optimal control. Okay. So these are the contents of today's presentation, and we'll be discussing what is basic conventional control and how optimal control is different and what is unique about this optimal control. And we'll see some of the core principles of optimal control. Okay. And then we'll dive into the applications of optimal control, and we'll see a case study, and then we'll discuss the challenges and limitations and go ahead, discuss the future possibilities, and conclude the presentation with the conclusions. Okay, so let's dive into it. Okay, so let's start with the basic structure. What is optimal control? So optimal control is a mathematical framework for designing control policies that optimize a system's performance. Okay, so there are millions of systems of different categories in the real life. Okay, so every real life based system needs a control strategy, because if humans are going to design something in hardware form, or even whatever the humans design in the first place, they want the system to obey them, right? So we need control strategies, and they should be realistic and they should be able to get the job done. So there are different, well, let me just. So there are different control strategies with different methodologies, but all of them follow a same procedure. Okay, so I'll just go ahead and guide you about that procedure. So here we have a block diagram that represents this basic procedure of control throughout the world. So in this block diagram, we have a block called the plant. Okay, so this plant represents any system that you are working on. It could represent a moving truck. It could represent an airplane. It could represent a tree. It could represent a house. It could represent an economic system of a country, or it could represent the speed of a motor. It could represent signals of something, maybe voltage, current, batteries, voltage. It could represent various kinds of stuff. Okay, even in biomedical engineering, it could represent uh, tumor of a brain tumor, someone's patient's brain tumor. It could represent that. So plant is something that you are going to work on, and you want some control over something that can be considered as a plant. Okay, so this plant is, well, not in our control at the moment. We introduce another block and we label it as the controller. Okay, so what this controller does is that, well, it gives a certain input to the plant to ensure that the output of the plant is as per our requirement. For example, if this plant was, for example, representing a brain tumor of a patient, right? So the job of this controller would be to give chemotherapy in such concentration over certain periods of time that the output is what we want. We want the patient to be cured. We want the brain tumor to be gone. So it's the job of this controller to give that chemotherapy in such a way that the patient is cured. Okay. For example, if this plant was representing the well, the forward motion of a and of an airplane, and the what we want is we want the airplane to go in the forward direction. So it is the job of this controller to ensure that the engines are running in such a way that the plane is moving forward. Okay, so plant could represent anything. This controller is something that ensures you get as an output of this plant what you want. Okay, so this controller will ensure that. So we have a plan that we'll be working on. We have some control strategy, which is called a controller, that will ensure what we want, but we need to tell it what we want, right? So we have another signal in this block diagram that is called the input reference. Label that xref, or you can label it iref. The symbol may vary from time to time. Okay, so this input ref is the signal that you tell the controller, you give the controller this signal and indicate your desiredness. Okay, so this reference value reference value is the something that you want. For example, if I say the reference value is maybe uh, 0, so I would say that I want the output of this plant to be 0. Okay, if this output was giving the concentration of brain tumor cells, I want the brain tumor cells to be 0. Okay, so I would give this 0 command, and it will be given to this controller in the input of the controller, and it's the job of the controller to give signal in such a way to this plant. This signal would be the drug dosage of chemotherapy, so in such a way that the output is achieved. Okay, so this is what we want, and the output is what we are getting. And it's the job of this controller to ensure that output is as per our requirement. And we have just defined the requirement. Then what we do is, how do we know if the output is as per our requirement or not? Well, we can observe it, but the controller should be able to understand or to observe somehow what is the output. So if the output is not as per our requirement, it can do some manipulations and try to get it as per our requirement. What we do is that we measure the output using some sensors. We can measure the health of the patient, we can measure the rpm of the motors, we can measure the thrust of the engine, or we can measure the current of the battery, or whatever the output we were talking about, we can measure it using some sensor. We call this sensor in generic terms feedback sensor. We measure the output and we compare it with the referencing. Okay, so when we do this comparison indicates it is the difference between what you wanted and what you are getting. Okay, so the difference between what you wanted and what you are getting is called error, error of the system. Okay, for example, you gave the input signal as the reference signal as 0, indicating that you want the output to be 0, and due to whatsoever the reason the output was 5, let's say. So we measured it, and this feedback sensor gave this 5 units back to the system. So here at this point, we have this negative feedback. We give the negative sign here. And so this indicates -5. And over here, we have +0 because we gave the zeros. So +0 -5 is equal to the error was -5. So this error indicates that you have to reduce by -5 units in the output to get what you want. Okay. So we always give error of the system to this controller. Okay, this error has the information.
Okay, I'm seeing that the presenter has frozen. The sound went fro It looks like he may have lost a connection here. I wish I could pause the recording. I can't pause the recording though. I don't have that control. Do I? No, I don't have the ability. To pause the recording.
So I'm back. Am I visible now?
Yes, you are back. Good. Thank you.
Yeah, I don't know what happened. The Zoom just closed.
Yeah.
Sorry. Okay, I apologize for this. So my screen is visible?
Yes, it is.
Okay, great. Okay, so I'll just carry on. Okay, so to sum up, what we understood was we have something called an error, which defines what you wanted and what you are getting. And we give this information, the error, to this controller where our strategies exist. And it is the job of this controller now to generate such a signal or give such a decision to the plant so that we get what we want. Okay. So this is the basic structure, the control structure of building anything. Okay. So So in this block, the controller block, well, I'm just stating for the moment that it is its job to generate such a signal in such a way that we get what we want. But since this controller is designed by humans, right? So we have all these strategies. We have basic controllers, we have linear controllers, we have non-linear controllers, we have traditional controllers, and then we have these optimal controllers, right? So there are different strategies to build some logics, some policies in such a way that this controller block is good enough to get the job done. Okay, so so now we can understand this first point once more. So optimal control is a mathematical framework for designing control policies that optimize a system's performance over time. Okay, so optimal control is basically some type of strategy that we will incorporate at the back end of this block. Okay, so that will ensure that the policies are designed in such a way that the decision is always intelligent enough to get the job done, which is get what you want in the output. Okay, so what's special about this optimal control? Okay, we could design any basic controller and it can be, well, it would get the job done, but if the task is complex, it may fail. So something unique about this optimal control is that it focuses on this error signal. It focuses on this error signal, whereas there's a lot of information about the system, because there's the information about what you want and what you are getting, and it also includes the information about the system as well. So it focuses on minimizing or maximizing a cost function while satisfying the constraints. We'll see what constraints are, what's the point of constraints, and how important are these constraints during the design process. Okay, so we'll go ahead and see in the case study that if you do not define the constraints of a system, well, your design is not going to be good enough for real life applications. Okay, so you always define some constraints. For example, if I were to design, well, if I were driving a car, okay, if I were driving a car and I rotate the steering wheel anti-clockwise, so I have to define a constraint on the tire that it should at max turn to 45 degrees. If I keep on rotating the wheel, it should not keep on rotating the tire. Okay. I have to define a constraint that maximum rotation angle for the tire or the range of rotation of that tire of the car is such and such. Okay. So you always define constraints of the system during the design process to get an intelligent and realistic uh, control strategy. Okay, so it also focuses on this something called a cost function. Well, cost function is a mathematical function that represents the some form of the error of the system. Okay, so our job is to minimize this function, because minimizing this function would indicate that we are minimizing this error, and minimizing this error indicates that the difference between what you wanted and what you are getting is going to be near zero. Okay, and that's the ultimate goal, where we want the output to be what we want in the what we have given as the input. Okay, so why is this even important? It enables systems to operate efficiently, adaptively, and intelligently. Okay, it is widely used in robotics, aerospace, energy systems, and much more. We'll see one or two examples in the case studies, and then you have a little more better idea of why go for optimal control, why not traditional control. Okay, so well, uh, the optimal and conventional control are quite nearby. Okay, they are very similar to each other, but you can consider optimal control as the advanced form of this conventional control. It incorporates all of the basic functionalities of the normal conventional control, but it also enhances the efficiency and the structure and the policies and the algorithm uh, by by introducing some extra features to the system. So the conventional control responds to errors after they have occurred. Uh, well, uh, the optimal control, well, it predicts the future and acts before those errors are going to occur. So it is a bit advanced version. So in conventional controls, we have some fixed parameters. We cannot have, well, it has limited adaptability. For example, well, if I have designed a vehicle, a car, okay, a motor car, I have designed for like carrying the weight of maybe 500 kg, okay. So if the weight is less than 500 kg, my car is going to go, well, work nicely. But if I will overload it, its control system may fail if I have designed it using conventional control. So that indicates that it has less adaptability to the changes that may occur. Okay. So optimal control is dynamic. It adapts to the changing conditions. For example, if I have designed, another example is that I've designed a UAV system, a drone, an aeroplane, okay, and it works great. But in the presence of a storm, okay, the drone was flying and suddenly a storm came in, and now there's a huge wind gust and huge external disturbances to the system. Now my conventional control will fail because it cannot adapt to these new conditions, but my optimal control will play a good role here, and it will adapt to that those changing conditions and work greatly. Okay. Okay, I hope my slides are visible as per. Okay. So then we, okay, so examples of conventional control is maybe we have some, heard of this PID controller or something, an on-off controller. And examples of this optimal control is some advanced techniques in this control domain, which is the linear quadratic regulator or model predictive control, right? So if we talk about the core principles of optimal control, well, it has three main features, three main tags that can represent the fundamentals of this optimal control strategies. Okay. So the first one is it has a cost function. Cost function takes information about the error of the system, and it, well, based on the information of the error of the system, it takes some decisions accordingly to get what we want in the output. So it quantifies system performance, for example, energy consumption, error minimization. It considers this cost function and designs the signals at the output accordingly. And then we have this objective functions, which defines the goal. What is the ultimate goal, right? So we define it in a flexible way. For example, I say that I want these RPM of the motor to be such and such, and well, that's the ultimate goal. So I don't care about the consumption of the battery or the energy it will take or the consumption of the fuel. I'm not concerned about any of that. What I'm concerned is, I'm concerned about only such thing, right? I can define anything and I can be flexible about the rest of the things. So I define my objective, and based on that, it concentrates on getting that objective done by manipulating the rest of the parameters. So, and then the third most important part is the defining the constraints. So we define some physical, operational constraints or safety limits, okay, of the system, and it considers all of these parameters. Then it proposes some strategy of how you can go ahead and design something which will fit ultimately to this controller block, and it will be such a good strategy that you will get a good output even in the presence of some external disturbances. If there are some changes in the environment, it will adapt accordingly and still get what you want. Okay, so these are some of the major components of the optimal control strategies, right? So we'll go ahead and look at the some of the examples of these cost functions. How do they look? Since I told you that these are some mathematical functions, okay, so that represent the information about the error or the energy that is being consumed, stuff like that. So these are some complex mathematical equations, but don't worry about this. We'll just give a brief introduction of what these are. For example, if I was more interested in, I wanted to get something done in a short period of time. Okay, I'm not concerned about who does it, how he does it, what energy is being consumed while getting this operation done. All I'm concerned about is getting it done quickly. Okay, I'm not concerned about anything. I'm only concerned about the time factor. It should be done in no time. Okay, so if I want that, what I would do is that I would create my cost function, which is also called the performance index for time. Okay, so it would look like something like this. So my cost function would be the integration of from one point to another point, which basically gives you the information about the duration of the task. So every time the control strategy is doing something, it will consider this cost function because that indicates what I want in the first place. I want to get the job done quickly, not concerned about anything else. Okay. Another example is if I'm not concerned about the time, I'm concerned about the consumption of the fuel. For example, if I were to design an autonomous car like a Tesla that can be that can drive on itself, self-driving car, and if I'm more concerned about the time from getting from, let's say, New York to Washington, I would say that I'm only concerned about the time. I don't care about the fuel. So the car autonomously driving itself and the control strategy behind it would use maximum possible fuel, and it will not care about the health of your car, the health of your tires or brakes. It will not care about anything. It will only ensure that you reach from New York to Washington in minimum possible time. If you define your cost function of that as defined is in this first point. But now, in another scenario, you said, okay, now what I want is I don't want to get early. I want to spend minimum amount of money on the fuel. So this control strategy, this optimal control strategy will say, okay, if it even if it takes 10 extra hours, we have to ensure that minimum gas is being used. Okay, so similarly, we have some extra advanced parameters, but uh, all of these functions define something that the user want in the first place. So it considers that and adapts to it and gives decision about this how to control the systems accordingly. Okay. So we'll not go ahead and look at the rest of the complex equations. If anyone's interested in this, I'll will answer those questions in the question answer session. Okay. Okay. So if we say, okay, let's just define an optimal control problem. Okay, well, today's session is about the optimal control. So if we were to define something technically in an optimal control way, what we would do is we would represent the system that we are working on in mathematical equations. Okay, we'll represent the system in mathematics. And the second step we would do is we would define the cost function, which would indicate what you want. Do you want minimum time? Do you want minimum consumption of fuel? Do you want minimum consumption of energy, or altogether you want minimum fuel along with minimum time, along with minimum energy consumption? So the control strategy will find the mean between everything and a good trade-off. Okay. So you define the system in mathematics, then you go ahead and define your cost function. And the third part is then you define the constraints of your system. Okay. Maybe you can define while on your journey from New York to Washington, maybe you can define the maximum speed of your car is 180 kilometers per hour or miles per second, per hour, right? So you could define the top speed of your car. That is a constraint. Otherwise, the control strategy would say go at 500 miles per hour. That might be not possible in with the car that you have. Okay, so you define some physical constraints, and you can also define that I only have 50 liters of fuel in the tank. Okay, so take decisions accordingly. So you define the constraints and limitations of your system, and the energy indicating the fuel consumption. You define the constraints, you define the cost function, and you define the mathematical expression for that system that you're going to work. So you define these three things, and these three things are good enough to design an optimal control strategy. Okay, because it is taking more information, it can give you better decisions. Okay, so if we talk about what makes optimal control intelligent, well, it has the ability to learn and adapt using real-time data. Since, for example, if we wanted minimum fuel consumption, okay, so and we defined a cost function using this mathematical expression. Well, according to the, well, maybe the traffic, or you are on a highway at high speed, maybe it's a downslope where the autonomous car can maybe well, use a bit less fuel and use the effect of gravity to speed up the car. It could make intelligent decisions according to the environment. If there is some change in the environment, it can adapt to it in real time. Okay, it can adapt, learn, and make decisions in real time. Yeah, well, that's the intelligence of optimal control. So, incorporation of predictive models and optimizing algorithms. As we have seen previously, that act, conventional control strategies act after the issue has occurred. Optimal control tries to predict the issue before it occurs. Okay, based on few parameters and few testing, and so we would define such intelligent strategies in this optimal control that it tries to predict the issue before it occurs and decides the control strategy, and at the very instant of occurring it already gives you the solution. So it behaves much behaves better than the conventional control technique and a lot of complex systems. So it has self-tuning and self-optimizing capabilities, right? So according to it again, this point goes again to the adaptability according to the change in the environment. Okay. So we have some examples of this optimal control, that is reinforcement learning in control systems. That's an example of optimal control. We have AI-driven predictive maintenance. That is an example of optimal control. So in wherever you see intelligent control, there is a huge indicator that the optimal control theory or the techniques that lie in the domain of optimal control, they are involved there. Okay, they have been used in this intelligent control system. Well, again, just to redefine, well, if we define things like these, while designing the complex strategies, we are under the umbrella of optimal control. Okay. So again, if I'm working on a drone, okay, and I want, if I'm working on a drone and I want to make to fly this drone, and I say that I want this drone to go from 0 meters height to like maybe zero from 0 feet to 100 feet in 5 seconds. Okay, so I'm designing such a control strategy for that. Okay, so my conventional control will say, okay, if you want to go to 0 to 100 feet in 5 seconds, that's great. You just give uh, 50 volts to the motors, and they should run at 70,000 RPM, and you'll get your job done. But that is the decision of the conventional control. In optimal control, I would define some extra parameters as well. I would say the maximum RPM of my motors is 20,000. The maximum voltage of my battery is 10 volts. Decide accordingly. In conventional control, you will get an answer that is unrealistic in real life. The maximum capacity of these motors was rotating at 20,000 RPM, but the conventional control could give you the answer of going up to 70,000. If you go up to 70,000 RPM, you would get what you want, but your physical system is bounded by its limitations. And the conventional control would say, give 50 volts to the motor. Well, I don't have a 50-volt battery. I have a smaller battery at my disposal for now. I will give this information to this optimal control strategies, and it will give me a decision accordingly. Okay. So here I have another example. Here we have an electromagnet, which is a magnet. When you pass current through the wire, it acts as a magnet, and the job of this system is to levitate this ball. It works something like this. We have an electromagnet, which is indicated by my hand, and we have a ball at the bottom of this hand. So gravity is pulling this ball, and this magnetic field is pulling it upward. So gravity is pulling this ball downwards, and the electromagnet is pulling this ball upwards. Okay. So I want this ball to levitate in free air. So this is only possible if the upward pull is equal to the downward pull of the gravity, right? So if I pass more current, the, the magnetic field is stronger, and the ball may just stick up to this electromagnet. So it has to be just right. If the current is so low, the magnetic field is so low, the ball will drop because the gravity force was strong. So I have to find the balance for that, right? So in conventional control strategy, I would give this information, and the conventional control strategy would give an answer something like this, maybe that if you give 50 amperes to the electromagnet for 2 seconds, you'll get your job done. But the battery I'm using is has the capacity of delivering maximum 10 amperes. I don't have 50 amperes. So in optimal control, before designing, I would define these parameters that the maximum limit is 10 amperes. So design accordingly. So it would say, okay, give 10 amperes for 5 seconds, then 4 amperes for 2 seconds, then 8 ampere for 7 seconds, and stuff like that. It would give you control decisions that are more practical and can be applied in real life. Again, we have some constraints examples. For example, the pitch angle, which is the tiltation angle of a drone. Okay, so if an airplane is flying, you have a certain threshold that the airplane can take only maximum of 45 degree. You can't make it at you can't if you want the plane to go forward, you can't make it at 90 degrees because it will go down. Okay, so you define some parameters, some constraints during the design process of this optimal control strategies, and it will design by considering those parameters. Okay, so these constraints play a huge role. Okay, because these constraints are giving the necessary information of your hardware. Okay, of your real life. These constraints are giving the information about that. So we need this information during the design process. So these controls are usually on two things. One is indicated by this X, which is the system's limitations. For example, the maximum RPM of the motor is 20,000. So these constraints are defined in this system's constraints parameters indicated by this X. And then we have something, another variable called U, which is the constraints on the input energy that you can give. That could be the battery which is being consumed by these motors. Okay. So energy giving to the system is the input energy, and external energy is that is going to the system is the input energy. So you may have fuel is an example of an input energy. Fuel is an example of this U variable because it's an external energy that is going to the system, which is the car. Okay. So U is an example of fuels in liters, and X is an example of the maximum rotation angle of that tire when you rotate the steering wheel. Okay, so I already gave this example. Yeah, mentioned in the next slide. The range for angle of rotation of a tire guide that I just discussed. And we have maximum angle of rotation for example, these are just few examples. So these are the elevators in an aeroplane. Okay, so it has a limitation. It can go from 0 to 50 degrees, 60 degrees maybe. It cannot go to 130 degrees. Okay, so I have to define that during the design process. Otherwise, my conventional control strategy could say, okay, you want that output, so just turn your elevator to 130 degrees, but it is not realistically possible. So there is no point in designing such a control strategy. So we should go ahead and design this intelligent optimal control strategy by giving constraints of the system to the control strategies and defining the cost function. The cost function and the objective functions define what you want. What is it that matters most for you? Do you want to get the job done in less time, or do you want less consumption of fuel? So you provide maximum information about what's the limitation and what you want. So the control strategies take decisions accordingly. Okay. So here also another example of I just gave about the ball, which is mentioned here. So yeah, so we understand it's a very good strategy. So well, like everything, it has some limitations, and that is this. Well, it has computational complexity since well the control strategies are sophisticated and they need high computational power. And if we are working on something which is simpler, well, it's easily executable. But if we go ahead and, for example, work on a fighter jet, it has complex dynamics. It would need supercomputers for computations during the design process. Hence, high dimensional problems, which indicates the complex problems, require significant computational resources, right? So, and one more limitation is this uncertainty in real life. Okay. So even though it can cater and adapt to the changes that may occur in the environment, but still it has a threshold, right? So, well, if there is a tornado, what can the control strategy do about a tornado? Okay. So it has some limitations in this because of this uncertainty in real world systems often have unpredictable disturbances, right? So, and then we have this well, challenging task of implementing this control strategy into the hardware. We have to translate the theoretical models to practical solutions. We have to consider the computation power of the processors, of the computers, of the electronics that I have in hand. Maybe my algorithm is quite nice, but it cannot be computed onto this cheap hardware available at the stores. I have to design some special chips, so maybe contact NVIDIA and go ahead and get some high-tech equipment to run these algorithms in the hardware. So, well, that's one of the challenges that we face normally as well. So if we talk about what can be done in the future about well this optimal control strategies and about the limitations that we just talked about. So We can integrate these strategies with artificial intelligence and machine learning. It will enhance the adaptability and learning capabilities, so it will make it more intelligent. Okay. So we understand that if you define the constraints and the objectives that you want, it's an optimal control. If you don't define them, it's just simple control. Okay. So once you have defined those constraints and the objectives that you want, it's an optimal control. Now, if you can maybe integrate machine learning algorithms with optimal control, we can even get much better decisions than using optimal control strategies on their own. Okay. AI or machine learning integrated optimal control strategies will give you much more better and intelligent decisions. So that is one of the future works, that we can integrate AI with this optimal, even though in today's world we are integrating AI with everything. So the second point is this quantum computing. We can use quantum computers to solve these complex problems, because we just saw that one of the limitations is that we can't, well, there's a lot of computation power that requires uh, solving the problems of these control strategies during the design process. We can use quantum computers, and we can also go ahead and use this edge computing, which gives real-time optimal control in distributed systems, which is a vast network, and we are working on something huge. So we can go ahead and make use of this edge computing as well. So, in conclusion, well, optimal control provides a powerful framework for intelligent system design. It enables proactive, which indicates that you are going to act before the issue has occurred. And it can provide adaptability, and it can learn the changes in the environment and adapt accordingly and define the control strategies in such a way that the control decision is good enough to get what you want. So it bridges the gap between theory and real world applications, right? So we understand if we define the constraints and everything, it would give the details. So it is practically possible to implement that theory. In conventional control, well, we face a lot of issue regarding this, that it was great, it was working in theory, but not working practically because we didn't give enough information. So giving enough information about the system, the constraints, and the objectives that you want, well, that changes the conventional control to a new heading called the optimal control. So future advancements will further enhance its capabilities. It's something that researchers are working on daily basis, and it will expect much more better strategies proposed by researchers throughout the world in future. So the concluding remark could be that optimal control is not just about efficiency; it's about intelligence in decision making. Okay. So that's pretty much it. So if we have any questions, we can go ahead and ask those. Up to Dr. Lambert.